In last class, I discussed what is function and I given some examples which are functions, which are not functions. In today's class, I'll discuss types of functions with illustrations. Here, first function, one function, a mapping f from A to B is said to be some other name it has injective if f of x1 equal to f of x2 implies or when x1 is not equal to x2 or different elements of A has different images. Here, what is the meaning of this? Here you have a one set which represented with a Venn diagram. Simply, Venn diagram is representing in the form of a circle. Here, two sets are connected by a mapping F. Here, element of A. Suppose you take two elements, corresponding image. That means 2 is different from 3. This 4, which we call it as f of 2 or image of 2. 6, we call it as image of 3. So this we also write f of 3. Elements are distinct, implies images are distinct. We say that function is 1, 1. Which is not 1, 1. What we say here is here you have a mapping f A to B. Elements are different. So 2 is not equal to 3, but f of 2 and f of 3 both are equal to 5. So here it is. This is not a 1, 1 function because distinct element has same image. So discretely we can say like this. But when problem comes, f map from R to R, f of x is x squared. Is f 1, 1. Something is true, you should prove it. Something is false, you should give examples. One example is enough to disprove. So here, real numbers. Here A is nothing but real numbers, B also real. Real numbers means negative numbers will be there, positive numbers also will be there. So f of minus 2 is f of 2 is we get 4. For two distinct elements, we have same image. So this function is not 1 1. So like this, he'll give the one example. He'll give the options like it is 1 1 or not 1 1. Next problem, f of x is x. Is f 1 1. But question must be, domain must be mentioned, range must be mentioned, codomain. Here, if you consider this function whose domain and codomain are real numbers, 0, f of 0 is 0. So 0 has image 0. Minus 1 has image minus 1. F of 1 has an image 1. So here elements are distinct. Image is also distinct. Therefore, function is 1 1. Let us consider the same problem. F map from R to R. I proved that this it is not a 1 1 by giving example. But here I'll consider the same function. I will change the domain. Instead of real numbers, only positive reals I take in the domain. Here you have a mapping of R plus to R. 1, it is 1. 2, it is 4. 3, it is 9. 4, it is 16. Element changes, image changes. So this function is obviously is 1 1. That means through this, look at this. Function is same in both cases. Here also function is same. But here it is 1 1. But here it's not 1 1. What is the difference? Difference is here domain is real numbers. Here domain is positive reals. That means by seeing function, I cannot come to a conclusion that it is 1 1 or not 1 1. So next here, one more example I give. F map from R to R, f of x is 2 power x. Is f 1 1, right? So generally, how do we check? We take domain means infinite numbers or real numbers is an infinite set which starts from minus infinity to plus infinity. If you take 0, 0, minus 1, 2 power minus 1, 1, it is 2 power 1, minus 2, 2 power minus 2, which is 1 by 4. So it's very clearly understood that function is 1 1. So this is one way. By taking few negative elements, zero, positive, can check different elements as different images. You can come to a conclusion function is 1 1. When it is 1 1, how to give a generalized proof? One is this. Other definition of 1 1 is whenever images are same, whenever images are same, functions must be same, elements must be same. Image means functional value. So I will prove this in other way. We have to assume that f of x1 is f of x. F of x1 is how much? 2 per x1, which is 2 per x2. 2 per x1 by 2 per x2 is 1. 2 per x1 minus x2 is 1. X1 minus x2 is 0, which implies x1 equal to x2. So I assumed functional values equal, then I come to a conclusion that function is 1, 1. So other function, f maps from r plus to r. I'll define f of x as log x is f11. What we have to assume, f of x1 is equal to f of x2. This is our assumption. Log x1 is log x2. If you can conclude that x1 is x2, here we can write 0, we can write log 1. x1 by x2 is 1. Therefore, we say f is 1, 1. Right. So now I given examples based on disproving that function is not a func 1, 1 by giving counter examples. How to prove that once function is given, it is a 1, 1 means this is the procedure. Second type of function, onto function. A mapping from A to B is said to be onto function if each element of B has pre-image in B, then we say function is onto. It has another name, surjection. Let us see to understand what I'm saying in the definition. So I'm considering two sets. One is domain, other is codomain. Mapping is defined as like this. 4 has a pre-match. One is called pre-image of 4. So 5 has a pre-match 2. 6 has a pre-match 3. Right. So here every element has pre-match. Therefore, F is on 2. So here, which is not on 2? Let us take 1, 2, 3, 4, 5. 3 has a pre-match 1. 4 has a pre-match 2. What is the pre-match of 5 means? There is no pre-match. So it is not on 2. That means there is some element in the codomain which is not having pre-match. It is not 1 function. So another example 1, which is 1 on 2, which is not on 2. Now, F map from R to R, let us take. Is F on 2 is the question. For that, in fact, infinitely many elements are there. Checking everything with every element is not practically not possible. Here 0, 1, 2, 3, -1, like this. So what is the pre-match of 4? So f of x is x square, which is 4. What does the pre-match means? 4 has a pre-match too. X square is 9. What is the pre-match means? 3. For 16, what is the pre-match means? 4. So corresponding to the functional value, what is x? Right. Suppose you want pre-match of 3. X equal to root 3. Root 3 is the real number. So there exists pre-match. So I have checked till now 4 elements which has pre-match root. But if I take -1, x square is equal to -1. So no real number exists. No real number which satisfies this equation. That means here minus square is +1. Minus square is any number square is plus. There is no real number for whose square is -1. Right. That means this function is not onto. If you are able to show, suppose there are 100 elements, for 99 elements there are pre-matches. For one element there is no pre-match, we say it is not onto function. So many elements here has pre-match, but there is one all negative numbers in this context, in this example, are not having pre-matches. So therefore it's not a onto function. Suppose if I take f as r plus 2r, same function I will take. Here, mapping is f, r plus and r. If you take, for example, 1 for 4, you have a pre-matched. For 3, x square is 3. Root 3 is the pre-match. Since negative numbers are there, not there, so we don't have any trouble. So can I say that each and every number has a pre-match? All positive number has pre, but there is 0 whose pre-match means x value, but the 0 is not there in R plus. R plus means open 0, closed infinity. After 0, 0 is neither positive nor negative. So 0 does not comes under positive real numbers. That means for this 0, there is no pre-match. Here there are infinite elements. All element has pre-match except the 0. Even one single element is not satisfying. We come to a conclusion that f is not onto function. So one more example I give. F map from r plus to r. F of x is log x to the base e. Is f onto is the question mark. Here f r plus to r. Here, for example, you take it as 1. What will be the pre-match means? Based on logarithm definition, e. Suppose you take 2. So pre-match means x square. X is e square. E square is a real number. No problem. Take 0. Here x is e power 0, which is 1. Take this as minus 1. X here is e power minus 1. 1 by e. Right. So like this. So every element has pre-match, whether it is negative, 0 or positive. Every number of codomain has a pre-match. So therefore, what I say is this function is onto function, right? So one more problem, let us discuss onto function. It all depends upon f map from n to r. F of x is defined as 2x plus. N here is natural numbers. Is f on 2 is the question. So what we have to do here is Here mapping is there F N to R. If you take for example 6, 6 is a real number, 2x is 3, x is 1.5. For real number 6, what is the pre-match? Means 1.5 is the pre-match, right? So if you take 8 here, some 7, 2x plus 3 is equal to 7, 2x is 4, x is equal to 2. For 7, pre-match is 2. For 6, pre-match is 1.5. But 1.5 is not a natural. Therefore, F is not onto. So, another question. Give an example of a function which is neither one nor onto. Suppose if I map like this, it is not a function because 4 does not have an image. Suppose if I give image, 3, 4 are distinct elements having same image 7. 9 has no pre-match. So therefore, F is not onto. So this is an example of a function which is neither one nor onto. One but not on. So here if you take like this, distinct element has distinct images, but 7 has no pre-match. It is an example of one but not onto. Onto but not one. Here if you take 1, 2, 3, Here, like this. Here, 6 has two pre-matches. One element can have any number of pre-matches. It is not on to, sorry, it is on to, but not 1 1 because two distant element has same image. Both 1 1 and on to. Here it is. Elements are distinct images. It